Now we're going to take a look at the difference between annual and continuous growth rates. So let's start off with a little scenario. Suppose we knew p equals p0 multiplied by 1.05 to the t, with t in years. We would actually say, as we learned before, that p is growing at an annual rate of 5%. That's our nominal rate, and that's our annual rate. If we actually had p equals p0, e to the 0.05t with t in years, we would say p is growing at a continuous rate of 5% per year. So both are 5%. The one is an annual rate, the other is a continuous rate. Notice if we did the math out and we computed e to the 0.05, we would end up getting 1.05127. Or in other words, we could write our continuous growth equation, our p equals p0 multiplied by e to the 0.05t, actually as p0, right, again our initial population, multiplied by the quantity 1.05127 to the t. So what that tells us is an annual rate of 5.127% and a 5% continuous rate generate the same increase in p. We would actually say those two rates are equivalent. So notice e to the 0.05, as we would expect, because we're compounding continuously, earns us a greater rate than just the 5% does. So notice, by the way, that the continuous growth rate percentage is always smaller than the equivalent annual rate. So in other words, you get more bang for your buck doing continuous growth than you do with annual growth. Now, what we haven't really said yet is, but we've implied, is the number of e has an important relationship when we talk about compound interest. And so we're going to take a look at that. Suppose we had $1 and we invest it in a bank account that pays 100% interest rate in 1 year. If I did the math, it makes sense, we'd get $2 at the end of the year, but we'd have $1 multiplied by 1 plus 1, remember our rate 100% would be the number 1, divided by 1 compounding, raised to 1 compounding in 1 year, and we do in fact get the $2. Right? So now what we're really looking at is our formula, and if I come back to our formula where we have the initial value multiplied by 1 plus r over n to the nt, if we plug in what we've just been looking at, we would actually have $1 multiplied by the quantity 1 plus 100%, or the number 1, divided by the number of compoundings, which we just used 1 in a minute ago, raised to the n times 1. The 1 is for 1 year, and the n is the number of compounding. So what I'm going to do is I'm going to look at what happens when I compound more and more and more and more times. So when I do that, I take that formula and I actually compound a number of times. So if I do it once, I get $2. If I compound it semi-annually twice, so if I used n as 2, I get $2.25. If I use quarterly, so that n was 4, I'd end up with 2.441406. And I realize that's not money, but it's important so I can look at the decimals here. If I did it monthly, so I plugged in 12 in for n, I'd have 2.613035. If I substitute in 365, the daily, it'd give me 2.714567. If I did hourly, which would end up being 8,760 times, and then I did each minute and each second, you'll notice it almost feels like the number is approaching something. If I kind of look at what I think of as fixed decimals, I have 2 point, and once I'm up at each second, notice what's kind of fixed is the 7182. And so one of the things that's kind of interesting to look at is what happens if I go to my calculator and I just do e to the first. And if I go to my calculator and plug in e to the first, I get approximately 2.718282, which is the compounding value I managed to just get for each second. What you don't really know that we did, but I actually just kind of did through the back door, is I've actually come up with a way for approximating the value of E. And this is actually where this particular number was generated from. It was generated from somebody looking at this formula that I looked at on the bottom of the previous page. 1 multiplied by 1 plus 1 over n raised to the n. So if I actually simplified that, made it not look so much like money. So if I take a look at this notation, what I've just done is I've looked at what happens when n gets really, 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 really large in the formula 1 plus 1 over n, all raised to the n. And so notice my notation. I'm using limit notation. This is very, very standard limit notation. I said, what happens to the limit? Where does the number go? That's what limit means. As n, the number of compoundings, or the n in my formula, gets really, 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 really large as it goes to infinity in the quantity 1 plus 1 over n to the n. And if I did that in my calculator, all as a single expression, and I just looked at a table, I would get approximately 2.71828, and it would keep going. And that is the number we define as E. And so E actually came from someplace. It came from this computation right here. So E is actually from a limit. When I first learned that in calculus, it kind of went over my head, but now I think it's really kind of neat that we have this number that's E, it's like pi, that type of a number, this irrational number, that comes from someplace, that I can figure out where to derive it from.